Welcome back to another episode of Learning Integration. This lesson will be focused on integration by parts and the function Ln of x. So we have the rule for the integral of Ln of x, and here we have the formula for by parts Lagrange's notation. So let's get started. Okay. Sure, if you want to look at it, you just pause the video. I don't need to wait. But let's start with our first example. So we have hx equals, we're going to start with x ln of x. Okay, so let's see what we got. Let's see what method we use. Substitutional by parts. Obviously I've suited these to by parts, but this is the steps you follow. Function times a function, yes. If inside the brackets of one of the functions, if I derive it, will it help me eliminate this first function? And the answer is no. If we derive x, it won't help us get rid of x, because we'll have 1. But then, if you don't use substitution, you use by parts. And if by parts doesn't work, then you're on your own. So let's find the integration of the integral of both sides. Capital, signify integral. And we just use the integrand symbol. X ln of x dx. Okay, so just like in my other video, in one of my videos, I showed that you pick the one that simplifies the best. Now, with ln of x, I found well, if you've watched my other videos, you know what I mean when I say I've picked the ones that simplify the best as being this fx. But in this case, with ln of x, I've found that you pick fx to be ln of x, because if you were to find the integral of ln of x, it would actually be more complicated and a bit of a pain. Okay, if you don't know what that means, that's fine, because the formula, we compare these two, this and this. So one of these has to be the derivative of gx, and one of these have to be just fx. Okay? That is because the next step is, when you use the formula, we need to know fx, gx, and the derivative of fx. We only have two of those. We only have fx and derivative of gx. We need gx, so we need the integral of gx, and we need the derivative of fx, so we need to find it. So we write up this little board. Okay? Now, we've got to pick one of these to be our fx and one of these to be our gx. If we pick this as fx and we derived it, sure, we'd get 1. That's pretty easy to work with. But if we had ln of x as g dash of x and we went to find the integral, it would give us this big lot of rubbish that would just be a pain to work with. So, if we found the integral of x, we wouldn't have a big catastrophe, but it wouldn't be simple. But if we have if we derive ln of x, it simplifies down pretty easily. Better than if it was integrated. Now that might not make much sense, but we're going to pick this one to be g dash of x. And we're going to pick this one to be our f of x. Remember, we're comparing it to this. So whatever we choose for this determines what this is going to be. That's the rest of the equation. So g dash of x is x, and fx is ln of x. Let's derive ln of x. We get 1 over x. Let's find the integral of x. We get x to the power of 2 on 2. Because we add 1 to the power, then divide by the new power. I'm not going to put a plus c, because I don't like doing that at this stage. Most people don't. You can if you want. It just makes more work for you throughout the process. I like to add my constants on as we get closer to the end, or at the very end. Okay? So now we've got this. This is good. Now we can answer this. So let's do that. Okay. Hopefully I can fit it in. Not really. Okay. So we've established that the start is x ln of x dx. And admittedly we've switched these around, but that doesn't matter. They're multiplied together, so it doesn't matter which way they sit. If they're multiplied together, you know, doesn't matter. You can have x at the back, ln at the front, all the way it is now. Anyway, we've got our answers here. So we're going to use them. Okay. fx. We've established fx is ln of x from here. Gx. We've established gx is x squared on 2 minus the integral of derivative of fx, 1 on x, multiplied by gx, gx being x squared on 2. Okay, now we have our formula and we can solve. Okay. This front bit basically stays the same. We're just going to bring the x squared out the front, ln at the back, and the 2 on the bottom just to neaten it up. And over here, subtract. We're going to fiddle around with this. We can get rid of this, the x on the bottom, and we can get rid of one x on the top. Now we're left to find the integral of x on 2 dx. Now, according to multiplication by constants rule, I'm just going to rewrite this. We can bring the half that this x is multiplied to out the front. Therefore, all we're finding the integral of is just x. I'm just going to write these little quotation marks because I don't want to have to rewrite this out every time. And now we're left the integral of x. We already said before, it's x squared over 2. Plus c. I like to add my plus c's in now, at this point, or at the end. Okay? Now we've got that. Now I'm going to write it out. And what we're going to get is x squared ln of x over 2 minus half multiplied by x squared on 2. We get x squared on 4 plus half multiplied by c, c on 2. We still don't know what the constant is, but now we know that it's definitely half of what it was in here. Okay. Now, what I'm going to do is I want to have this and this to the same base. First, I'm going to make a rule that h equals c over 2. Therefore, when we rewrite this, we can just write h. We don't have to have rubbish on the constant. Okay? If you write this in a test, and that h doesn't interfere with anything, then that in my experiences, is good. You're not in any trouble. I just don't like having fractions and whatnot on my constant. But how can we get these to have the same, the bottom to be the same? Well, we multiplied 2 on the bottom and 2 on the top, and we have a 4 as a base and a 4 as a base. I'll show you what I mean. 2x squared ln of x over 4. 2 over 4 is still the same as 1 over 2, but we want the bases to be the same. Okay, so we're left with that. Plus h, because I said h is that. Okay, now we've got that. We can make them have the same base, so we're left with 2 times x squared times ln of x minus x squared over 4 plus h. Okay? And I'll do it here. What I'm going to do is I'm going to factor out the x squared, because we have an x squared multiplied on this side of the subtraction and on this side of the subtraction. So we'll have x squared 2 ln of x minus 1 over 4 plus h. And that is simplified. And we've established that that there is the integral of, what did we say at the beginning? X ln of x dx. So this here is the integral of x ln of x. Now let's go on to one more example. We use trigonometric functions in this one. Example 2. hx equals sine x multiplied by ln sine x dx. Okay, now this is weird. We've got, well, and I did a previous video where I had sine x, I had cos x multiplied by ln of sine x. In that way, you can do substitution, because if you derived in the brackets, you would be able to eliminate the cos out the front. But we have a sine x and a sine x. Therefore, if we derive this, we wouldn't be able to eliminate this. And so we use integration by parts. Okay, so you find the integral on both sides. Okay, now we found the integral. We're going to use this rule at the beginning. Just like before, we're going to use this and compare it to this. So we're going to pick one of these to be g dash of x and one of these to be fx. I'm going to do the steps just like we did before. I'm going to pick ln of sine x to be fx, and I'm going to pick sine x to be g dash of x. Because in my experiences, it works out always better if you pick the ln of sine x to be the fx. So we'll write that out. fx equals ln of sine x, and the derivative, and we'll write the gx, and we'll write g dash x. Now we've labelled g dash x as sine x. Okay? Now, what's the derivative of ln of sine x? Well, when you derive, this is just using the chain rule. So, derive the outside, we're left with 1 over sine x, and then multiply it by the derivative of the inside. So the derivative of sine x is going to be cos x. So I'm just going to skip a few steps and write this, because 1 over sine x multiplied by cos x is cos x over sine x. That's just it. Okay? Now I know this is trigonometric identity. It will equal, I think it equals like cosec or cotangent or something like that, but I'm not going to write it. I'm just going to leave it like that. Okay? So, now I'm going to find gx. Integral of sine x is negative cos x plus c. I'm not going to write the plus c. I don't like doing it at this stage. I've already said that. Okay, so this is what we've got. Integral, should be more straight, of sine x multiplied by ln of sine x dx. And that equals, well, we're using this. We're going to be using this as a little guideline. I'm running out of a bit of room on my table. Okay, so fx is ln of sine x, gx negative cos x, might run out of room, subtract the integral, I'm going to bring it down here, f dash of x, cos x over sine x, multiplied by gx, gx being negative cos x dx, or just enough room. Okay, now we've got what we need. It's a bit tight, but that doesn't matter. Now we're going to rewrite it. I'm not going to write this bit because I've already written it, so I'm just going to put the equal sign over here. ln ln of sine x multiplied by negative cos x is just negative cos x ln of sine x. Now, subtract. Okay, so because we have a cos x multiplied by a cos x over sine x. So that's cos squared x on sine x. It's actually a negative, but multiplication by a constant means that we bring the constant, brings the constant in front of the integrand symbol. The constant here is negative 1, because negative 1 multiplied by cos x is negative cos x. I hope this makes sense, but I'm going to bring out the negative 1. And therefore, if we have subtraction here, a negative 1 multiplied by a negative is a positive. So it'll look like this. Okay, this would be negative cos squared x, but because multiplication by a constant, I brought the negative 1 out and multiplied it onto the negative that was already there, which makes it a positive now. See, negative, now it's positive. Okay, now we're left to deal with this. Okay, so we can just rewrite this a little bit out here. Negative cos x ln sine x plus. Okay, so there's a trigonometric identity, and I'll write that on a separate page. 1 equals sine squared of x plus cos squared of x, and that's the trigonometric identity, equals 1. Okay, now we can rearrange this to get cos squared x on its own, and all that is we just have sine x. We have 1 subtract sine x squared, because I'm just subtracting sine x squared on the other side, and it will look like this. We have a cos squared x, and we have a cos squared x. Cos squared x equals 1 minus sine squared x. Therefore, we have integrand symbol. We have 1 minus sine squared x over sine x dx. Okay. So, what's the next step? Well, I'm going to split this. I'm just going to use these quotation marks because I don't want to have to keep rewriting this and waste time. Let's split the fraction and have 1 over sine x multiplied by sine x sine squared x over sine x, and the dx. Okay, now this will cancel the squared and get rid of it on the bottom, so we're left with 1 on sine x minus there's no multiplication, sorry, it's a subtraction. I'm getting a bit tired, but we have a subtraction here, so what I did was I split it. I have a 1 over sine x minus sine squared x over sine x. Now I've gotten rid of the squared, and because I've gotten rid of the 1 on the bottom. So get rid of 1 on the bottom, get rid of 1 on the top. We're left with the sine x on the top. And because integration using the rule of subtraction, we can split them up. And we're left with sine x dx minus the integral of sine x dx. I hope I haven't confused you too much or dragged this out a bit. I probably have dragged it out a bit. I'm just going to rewrite quotations because this stays the same. But over here, now we split it up, so we find the integral of each one separately. Okay? We're going to need another sheet of paper. This will equal, use quotations again, plus 1 over sine x is the same as cosec of x. Okay? Minus the integral of sine x will be, it'll be negative cos x plus c. Okay? So, rewrite quotations because we know what that means. It's written up here. Plus, what's the integral of cosec of x? It's a bit of a long one, but it's negative ln of cosec of x plus cotangent of x. And because we have a negative multiplied by a negative, that's a plus cos x plus c. Now the integral of this includes a plus c, but I ran out of room. Okay, I'll put that in at bottom. So what we're left with, if I rewrite what we have up the top, cos x ln of sine x plus, well, I'll write negative because we have a negative here, negative ln cosec x plus cotangent of x plus, I'm going to say c2 because we're adding a constant, but it's different to this first c, plus cos x plus c1. I should have written the c in here, but I'm writing it down here. Now this is starting to look like a big mess, and it basically is a big mess. But I'm going to write cos out the front, because this is a positive cos, and we don't want any of these going out because it's a negative. Subtract cos x multiplied by ln of sine x. Subtract ln of cosec of x plus cotangent of x. And I'm going to say plus c3. And we're going to say c3 is equal to C3 is equal to C2 plus C1. Therefore, I can write C3 down here because we have a C2 plus a C1. Okay? Now I'm going to add one more step, and that's just simplifying it because you can. This video has gone on a fair bit, but we're going to have cos x 1 minus ln of sine x so subtract ln of cosec x plus cotangent of x plus c3. And that there is as simplified as it's going to get. I would write in what we started with, which if we go a few pages back is going to be this function. I would rewrite that in here, but I haven't got enough room. I hope you learnt something. That was a bit long, but thanks for watching and I hope you had a good day.